So, welcome everybody. Today we are talking about geometric sequences and series. So these are different than arithmetic ones. Arithmetic ones had a common difference between our successive terms in our list. So most of our notation is going to be the same. A sub 1 is going to be the 2 here, right? A sub 3 is going to be the 18, all that. Except instead of a common difference, D, we're going to have a different variable, which is going to be R, representing the common ratio. All right. So does anyone see a pattern in this list currently? I mean, I only gave you three terms here.
Doubling,
Three.
tripling each.
Yeah, it appears to be tripling each time, right?
You
So
multiply it by 2 billion.
So multiply by 3, multiply by 3. So the next term in the list theoretically would be, what's that, 30 plus 24, 54, I believe, would be our guess, right? My guess. Anybody disagree? No?
Next one would be 54.
So the common ratio, denoted by the symbol R, all right, is, how would I describe that? The number you multiply each term by. Oh, all right, there we go. The number each term is multiplied by.
Hang on.
Don't worry, I'll pause once I'm done. Each term is multiplied by in order to get the next term. Right? And this type of sequence is geometric. I'm not even going to write that one down. But could someone give me a formula to calculate what R would be if I didn't know what R was in this case? Because you guys probably looked at the list and were like, 2 times what is 6? Right? But what's another way I could ask that that would be a little bit more formulaic and less intuitive? Any ideas? How did we find the common difference with arithmetics?
Now we're going to divide.
Yeah, I'll divide 2 consecutive terms, right? 6 divided by 2 is 3. 18 divided by 6 is 3. 54 divided by 18 is 3. So if I divide any 2 consecutive terms, so a sub n divided by a sub n minus 1, this minus 1 is a tiny minus 1, right? Hanging out with n down there in the subscript. So if I divide any 2 consecutive terms, the former from the latter, all right, I could find out what that common ratio is. So what is the R?
Wait, the former from the latter? Don't you mean the current from the latter?
Well, I'm dividing the former term. Nope. Yep. Thank you. That's what I get for English speaking. Former and latter, I guess, would be the same thing. You're right. So I'm dividing the former from. No. Former and latter. Yeah. Former from the current one. Yeah. Whichever way you say it. I think I'm saying it right. Well, either way, a sub n divided by a sub n minus 1. Right? We're all in a math class. We don't need the English to describe this. Right? Maybe?
Right.
Oh. Whatever. So there we go. So once I know the common ratio, I could even then, multiply 54 by 3 and get the next term. And what's that? 150 plus 4 times 3 is 12. So 162 would be the next one. Right? And you could do this over and over and over again to get, infinitely many terms in our list that all happen to follow this geometric pattern.
Yeah. Forever. You know, from the episode where SpongeBob went on strike?
I was thinking of the next day, and the next day, which is the
Next
episode in which I
Next
believe
day.
Mr. Krabs switches bodies with Plankton,
Well,
Yes.
where Miss
and then
where
he's the
Plankton
one that's
you-
trying to sabotage and steal the Krabby Patty.
the one where Miss
those
where
were,
Plank yeah the one where
wanted to get the Krabby Patty formula.
yeah the what
So we know this machine at least.
Right, yeah, just to see
Yeah,
if
the
he
one-
could do it. Like, did they have a bet or something?
well actually what happened was Plankton used the switch lives with someone just to know what it's like machine.
That's what it was, right. Or there's, of course, the line from The Sandlot, I believe, when he's like, forever. I don't know, anybody know that one?
I don't
That's
know.
a little bit more old school. That's more like my age bracket, but anyways. But those are all good references, of course. So let's see. So clearly, you guys can anticipate what my next step in this would be. What happens if I want to find the 100th term in this list? Right? I don't want to have to multiply by 300 times. That doesn't sound like fun. Right? So let's see if we can figure out what this pattern would be. All right? So let's see if we can derive a formula. All right? So my first term, a sub 1, would just be a, right? We did this kind of yesterday as well. So here's my term, and I guess I could call this formula, kind of, quote unquote. Right? So a sub 2, how would I find a sub 2? R, right? Right? And a sub 3 would be
AR squared.
which would it be? A times 2r or a times r squared?
AR squared.
Right, because multiplying this by another r, yeah. So ar squared, and then a sub 4 would be a times
R to the fourth. I mean third.
r to the third.
Yeah.
And let's see, maybe do I need to take another like 5-minute break in the video and pause like we did yesterday conveniently, which hopefully is edited out by now so no one on the internet knows that it really happened.
You could try looping a part of the video so that no one knows, like in the movie Speed.
We could do that in the video as well. So a sub n is going to be what, do you suspect? A times r to the n minus 1th power, right? So that's not minus 1 down there, it's minus 1, like a little micro subtraction there, right? So I believe we've derived our nth term formula. A sub n, the nth term in a geometric sequence. Notice it's the same exact symbol, but we have to recognize what type of sequence we're working with, is going to be a times r to the n minus 1. So nth term in a geometric sequence. So what do I need to know? I guess I could call that a sub 1 if it helps, right? So the things I need to know, I'll need to know the first term, I'll need to know the common ratio, and I'll need to know the number of terms, the n, right? So lots of the same variables, so this stuff should be pretty easy. So let's do an example. Exemple. Let's see, what if I've got this pattern? What if I've got, I like having tricky ones here. What about 12? And then 8? And I almost don't want to show you the next one yet.
16 thirds.
Maybe. So if I told you that this was geometric, and I want you to find the, let's say, 10th term. Yeah. Now, these with exponents are probably going to be a little bit more calculator heavy than our previous problems from the arithmetic days. So let's label what we know. What do you know? I like it. And now, just to point out, if this was like a short answer question on, say, like a quiz or a test, tell me what we know. Like, label everything. All right? Even if you know what you're doing, label everything.
N equals 10.
Right? N equals 10. I like it. That can give.
R equals 2/3.
How would I find r?
8 divided by 12.
8 divided by 12, which is 2/3. So there's my r value. Intriguing. And I don't know what a sub 10 is yet. Right? But labeling what I know, it at least is something I could give you partial credit for if you make a mistake or something.
So do we need to label what we don't know? Like
No,
a
you didn't
sub
have to
10
label it.
equals question mark?
Nah, you don't have to do that necessarily. But sometimes it can help you narrow it down, that sort of thing. So let's plug this in the formula. So a sub 10 is going to equal 12 times 2/3 to the 10 minus 1, right? 10 minus 1th power. So this is 12 times 2/3 to the 9th.
Ew. That's disgusting.
And in order to avoid decimals, which we could, this is 12 times, and by the way, I can't cross-cancel this yet because this one has to have the exponent apply first. That's 2 to the 9th over 3 to the 9th. So let's see, I'm going to figure out what 2 to the 9th is. Is that 5? That's what I was just going to say. And I'm going to multiply 512 times 12. 6144 over 3 to the 9th is 19683. So there's the 10th term in my list.
So 19683.
That's not bad.
Right?
I think we're going to divide both of those by 3.
Oh, yeah, you're right. Yeah, because 12 had the 3 in it. I should have canceled. You're right. Shame on me. So I guess I could have
6,560.
I could have made this 3 to the 8th and then made this 4. So then that's 2 to the 11th, right? Which would be 2048.
Yep.
Over
61. Because 4 is 2 squared, 2 squared,
Yeah. Sorry, or you could just multiply it out. Yeah. 4 is 2 squared. 2 squared times 2 to the 9th. So the internet can hear it. Add the exponents 2 to the 11th. And I don't know 2 to the 11th off the top of my head. I just know that 2 to the 10th is 1024. Because of computers. Bless you. Right, so that did simplify there. So yeah, good call, good call. Right, so I'm able to figure this stuff out. And I just use a formula. And I just want to point out, for geometric sequences, my numbers are getting smaller anytime my r value is less than 1 but greater than 0. And we wouldn't consider it a geometric sequence if r was exactly equal to 1, because that wouldn't be a very interesting sequence. Why? Why would that be a boring sequence? And what would that list look like? It'd be the same number over and over and over again because it's just multiplying by 1. So when r is greater than 1, this list would be growing. When r is less than 1, it would be shrinking. If r was 0, my first number would be whatever, and then the rest would be 0. So that wouldn't be a very interesting list either. What about when r is negative?
It'll go positive, negative, positive.
Yeah, we'd have alternating signs, right, where every other term would be positive or negative. Maybe I'll do an example of that real quick. Let's.
I'm going to say oscillate, but I think that was the first word, so it's like
Oscillate.
switch.
So let's see. Well, oh man, I could have some really interesting. I think I just thought of 2 really cool examples. Well, let me do this one first. So what if I've got negative 3, comma, positive
4, 9, 27, 81.
positive 4?
No.
No, not again.
You want me to avoid fractions? I will. All right. How about positive 6? Negative 12, I believe.
Yeah.
Dot,
And
dot,
then
dot.
positive 24.
So let's find a sub. I don't know. Let's find a sub. Let's just go to the 8th. So a sub. Oh, wrong color. So let's label what we know. So a sub 1 is negative 3. N is ocho. R is... All right. And you can divide any two consecutive terms. All right. So if for some reason the first two look like ugly fraction math, divide the next two or something like that. And they'll all give you the same common ratio. And I'm looking for a sub 8, right? That's what I'm looking for. So let's plug it in. And I'll have a sub 8 is equal to negative 3 times negative 2 all to the 8 minus 1th.
That looks like 98.
It does.
I know, all my A's always go.
Yeah, my A's slowly evolve into 9s at some times. I don't know. So, so let's see. What am I getting? Sorry. Negative 3, negative 2 to the 7th. Now, question. Is negative 2 to the 7th going to be positive or negative?
Negative.
Why?
Because it's an odd exponent.
It has an odd exponent. Is the 8th term in this list going to be positive or negative?
Positive.
Why?
Because...
But if you're multiplying by another negative.
Perfect. So this will be negative 3 times negative 2 to the 7th. I don't know that one. Is that...
128.
All right. I think I might buy that. 2 to the 6th would be 64. Okay. I'm trusting you on this one. And it's going to be positive something.
300.
360 plus 24. 384, yeah. All right. And then the next term would be negative. And the term after that would be positive, right? All sorts of stuff. Okay? How about this? I don't think this kind of problem actually exists, but I just thought of it, and it relates to the section that we just emerged from, the zone we just left. So let's say I have this list. What if I've got...
Oh, so we're on the opposite side now?
Yeah, that's what I just flipped my page. It is convenient that my pages happen to line up pretty good with the size of your page. So let's have, say you have a geometric, and I'm asking, how many terms are there? All right, and suppose it starts with, all right, so suppose my list starts with, let's do 36, and then dot, 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 and ends with 1/36. Now, it wouldn't have to be as nice as this one ends up being, right? But, so we could have all...
It's 136. The R is 136.
Is it? We don't know. Well, there's an unknown number of terms in between, I'm saying. Oh, I guess I do have to know the R value for that too, don't I? That's why these problems don't exist. Because it gives everything else away. Nah. Blast.
Hey. What?
Because it would have to be kind of like a...
I have to give you more than...
Yeah, we need one more piece of information. Because technically, no matter how ugly these became, it could work for any number of terms in between there. As long as it's at least one. Right, yeah. Okay. Well, I'll let you know what I was going for anyway. I was hoping to have a problem like this. where my unknown was in the exponent, and what would I have had to do in order to find that unknown? I would have had to log both sides at some point, because logarithms are the only thing that can solve for a variable in an exponent. But in this case, yeah. I guess if I knew my R value, but I didn't think that far ahead. Well, could we? I don't know. What if I make it super friendly? What if I told you?
But you could still have an infinite number of.
Right. What if I told you R was 1/6, and that I was ending at 1/36? Yeah, I think that'll work. Let's see if we can do this. Let's set it up. Humor me. So let's see. So my first term is 36. A sub n, because I don't know what n is yet, is 1/36. 36th, singular, I guess. R, as I said, was 1/6. And I want to know what n is. Let's do this. So I'd have 36 nope. 1/36 equals 36 times 1/6 to the n minus 1. So what should I do to both sides first? Ugh.
Yeah, at first glance it looked like it would just divide to 1 over 1, but then
No.
wait, that's the denominator.
So that's 1 over 1296, apparently,
Yeah.
according to Texas Instruments, to the n minus 1. Now what do I have to do?
Log.
If there was a base that we could work in that would be the most amazing, what would it be?
And
No.
1/6.
No. Well, maybe.
10.
Or log base 6 would actually be the best one to work with, since all of these happen to be powers of 6. And arguably, we could solve it without calculators using log base 6. However, we'll just use log, regular old log both sides. So log of 1296 equals, I'm going to pull the n minus 1 down for sake of time, because I got to actually teach one more thing. Log of 1/6. Right, so using my power property, I was able to swipe that down. Then I'll have log of 1 over 1296 equals n times log of 1/6 minus log of 1/6. Ideas, friends?
Add log of 1/6.
Yeah, it's a little ugly.
Hang on, I can't keep up.
Yeah. Oh, don't worry. This is like a extra problem anyway. You won't have anything like this tonight. I don't think. And log 1/6 equals n times log 1/6.
Add their log 1/6.
Ugh, man. Logarithm problems just have so much writing. At least they don't make you write logarithm 1/6 every time.
So it'll be
That
1
would
plus-
be horrible.
So-
now,
Calculator time.
all you have to do would be log of 1 over 1296 over log of 1/6. And that would have to be the whole.
Yeah, yep, you're right. And actually, log of this divided by this is the same as the log of their difference. So that's log of 1 over 1296 minus 1/6. And I could technically do a whole bunch of work there. I'm just going to plug this into the calculator, hopefully quickly, maybe not. Log of 1 over 1296 plus log of 1 over 6, close parentheses twice, divide by log 6, 1, no, 6, yep. And I get n equals 5. Meaning that 1/36 was the 5th term in that list. So that is far beyond what we would need to do, but I just want to point out we could even solve a problem like that.
So what song were you like humming to?
I don't know. I just made it up on the spot. I'm talented. If you wanted to forward, say, this YouTube video to some sort of agent, you could. Just saying. Maybe. Let's see. For sake of time, originally I was going to do this derivation on our own, but I think I'm going to just swipe it from El Libro, and I'll explain it to us so that way we can jump right into this formula. Okay.
Oh my god, that is hideous.
And I guess it saves us all some writing, doesn't it?
Yeah, do I need to write that down?
Nope, I'm just going to verbally explain it. So this is another derivation, or what did I call it yesterday? Discovery? I'll call it a discovery. So check this out. So here is our formula, or our. So, all right, really bad. We are going to try to find the sum of a list of a geometric sequence. We're going to try to add up all the terms. All right. So the sum of this list, in our basic understanding, would be the first term plus the second term plus the third term plus the second to last term plus the last term, right, all the way through, right. So we start with that basic premise, and we represented each of those terms by the formula a sub n. I think I've got some friends using cell phones over there. And I know I'm not live streaming this video, so it's not like they're watching my Justin.tv account on their cell phone and entering questions in the chat room. So, well, actually, wait, I lied. I am live streaming this. So, but you didn't say that was your excuse. Too sharp for you, maybe. That's weird. I forgot I was live streaming this. There could be some weird person on the internet watching me right now. What? I don't have my chat room open, though. They can't communicate to us. Wow.
They can still watch though.
They could. Actually, in StarCraft 2, since a lot of people live stream their matches, there's stream sniping, where like when you get randomly matched with like a Masters level player, you'll like be like, oh, I know this person, and I know that they stream all the time. So you'd like open up on your other computer or like alt-tab it and open up their live stream, so then you could see them playing against you and like keep alt-tabbing between them. So then you're essentially cheating. It's like screen looking over the internet, I guess. But they're broadcasting it, so it's their own fault. But stream sniping. There you go. So anyways, so someone could stream snipe this whole derivation right now.
Screen peeking.
Yeah. So here we go. So what they end up doing is they multiply both sides of this formula by r. So they get r times Sn plus, and then what do we get? A sub 1 times r is now a sub 1 times r. A sub 1 times r times another r would be a sub 1 times r squared. And everything's basically like shifted now. You see that? So a sub r to the n minus 1 times r is now just a sub 1 times r to the n, right? So then they subtract these two equations. So watch what happens when I subtract these, right? Beautiful thing, right? So Sn minus Rsn, okay, that's what we get here. A1 comes down. A1r minus A1r is 0. A1r squared minus A1r squared is 0. A1r to the n minus 2 minus A1r to the n minus 2 is 0. They all cancel out. And the only things I'm left with will be A1, and I'm subtracting this, so that's why it would be minus, right, A1r to the n. Okay? Does everyone follow that step? We get that?
Yes.
It's similar to what we did last time, yeah. Except the last time, what did we do? We added them together, and we added the same equation together for both. This time we multiplied by r first, right? And then subtracted them. All right. Good news, Internet. Student has marker on their face, but the problem's being solved right now. You need to... I don't see any. Maybe it was a prank the whole time. Some sort of, maybe it was a cyber spoof. I don't know. I wouldn't lie to you. Terrible. So anyways, so here, check this out. So we're trying to solve for Sn. So what they do is yoink, yoink, they factor out an Sn and get Sn times 1 minus r. And then to get Sn by itself, they divide both sides by 1 minus r. So either way, we end up getting our formula a1 minus a1 times r to the n all over 1 minus r. And that will be the sum of a finite sequence, geometric sequence.
What about infinite?
We'll be doing that in the next section. We'll be finding the sum of an infinite sequence. So crazy.
Sounds confusing.
Yeah. I love it, though. I love it.
That's impossible.
Yeah. What I should have done at the beginning of the year is just been like, hey, guys, add this list of infinitely many numbers. And then, like, by the end of the semester, like, you guys would, like, still be adding. And we'd see, like, who got the closest. And then I would just swoop in then in this chapter and be like, well, bam! And then, like, drop the answer on you, like, super quick. It would have been great.
Yeah, just imagine what like first graders or second graders might think if they saw us doing this. They'd probably be like, "That's math."
Yeah, I love it when math becomes more letters than numbers. It's a thing of beauty. And then when some of those letters become Greek.
Or when we start writing,
I love it.
what can be considered words. Cosine, sine, tangent.
Yeah, it's true. So let's see. Let's find S sub 10, right? So the sum of the geometric series. It's a partial sum, right, of the first 10 terms, right? And let's have our list. I don't know. I'm running out of ideas. What if my list is 1, 1.5? What would that be? 2.25, is it?
The decimal point in 1.5 is hard to see.
True. It's 1.5 times that. I think I got that right? Yeah. That's 9/4 if I was doing this fractionally. So let's see. So let's find S sub 10. So this is our last example. So for the S formula for a geometric, what values do I need to know?
A1.
I need to know A1. Do I know A1?
1.
A1 is 1, okay? So I actually use A1 twice, oddly enough. What else do I need to know?
R.
R? Okay, so what's R here? How do I find that? 1.5 divided by 1, so R is actually just 1.5, all right? I need to know N, which is 10. Notice in the arithmetic sum, I needed to know the first term, the last term, and how many terms there were, but I didn't need to know the common difference. In this one, I need to know the first term, I need to know the ratio and how many terms there are, but I don't need to know the last term. So I don't actually have to calculate, like I didn't have to figure out what is A10 first, right? So I can actually bypass using a whole formula where yesterday, if this was arithmetic, we would have had to use 2 formulas. Question, comment?
So when finding R, if the first term is 1 and the second term is some other number, do we really have to write down the division?
No, I agree that this could be done. R can usually always be done in your head, but I'm just writing it out for the sake of our notes. So let's see. So I'll have 1 minus 1 times 1.5 to the 10. And also I want to point out the thing that people will mess up on this formula is they'll do n minus 1, but it isn't for this formula. Okay? It's n minus 1 for the finding the 10th term, but it is not for finding the sum. And then I'm dividing by 1 minus r. And this one, oddly enough, a lot of people will be messing up their PEMDAS. A lot of people will look at this and be like, oh, 1 minus 1 is 0. 0 times this is 0. The numerator is 0. No. Okay? You have to kind of calculate all this before you do the subtraction. So I just want to point that out. So this is 1 minus, what is 1.5 to the 10th to the 10?
15.
I find that amusing. 57.665. all over 1 minus 1.5 is going to be negative 0.5, right? One minus second answer. So this is negative 56.665 over negative 0.5. So this is clearly going to be positive when those signs cancel. I like that. You could just double that number, right? Dividing by a half is the same as doubling, which is 113.33. 01, I guess, if you want my calculator's approximation of it. And actually, technically, well, I guess I started with decimals here, so a decimal answer is fine. And this is an approximation in this case. But yeah, so only if the original problem had decimals in it. Well, or, I don't know. We'll see. Yeah, I guess for this would be pretty gross. Having to, have done 3 halves, raise 3 to the 10th, 2 to the 10th, subtract those, you'd have fractions. These would have been fractions. Then, you would have had fraction over fraction. It all would have worked out. It would have been a lot of work. But you won't catch me on recording saying that I'd allow you to do that, but... So anyways, so that's today's lesson, geometric sequences and series. Bye-bye.